Okay, guys, so this is the last exercise and the last idea in the book here. This is 15J. This is, again, talking about the traveling salesman problem, but this is the second algorithm here. This is finding the lower bound for the traveling salesman problem. Now, remember, there is no perfect algorithm solution, especially when n gets high. You can check through all possible routes when n is quite small, but as soon as you get up to numbers like n is 100 or something, this is impractical to have an algorithm which deals with it. So we've got a lower bound algorithm, and combined with the upper bound algorithm, if we find the best lower bound, best lower bound and the best upper bound, and we bring that one in as well, then then we can trap our solution, hopefully, between two quite close values. And then we know that our best solution would be anywhere between those two things. So if we can find anything better than the actual upper bound solution that we found, then it might exist and brilliant if we can find it, but we're only required to find the lower bound and the upper bound. Okay, right. So what is the lower bound one? Well, the lower bound algorithm is called the deleted vertex algorithm. So it says, choose a vertex, remove it. Remove all of the edges incident to it from the graph. Then create a minimum spanning tree for the subgraph which remains. And then part 3 says a lower bound is the weight of the minimum spanning tree plus the combined weight of the two edges of least weight removed in step 1. If you repeat this process, then you will find the best lower bound. Okay, now we didn't repeat the process before. Remember, in the previous nearest neighbor algorithm, if we want to start and finish at A, we only have this one algorithm which we follow through for A. But potentially you could start and finish at different places, and you could check that. But normally the traveling salesman problem requires us to start and finish at a particular point. In this case, we're going to need to check through and repeat this process with other vertices as well, unless the question says otherwise. So let's look at a question. And I think this is the only question which we have before 15J. So again, last example in the book. So let's take this one here. My scruffy working out from the last bit. Okay, so find a lower bound by deleting A. So they don't require us to find the best lower bound here. So they don't require us to repeat step 4 in the process by going around to all of the other vertices. But of course you could, but it would take quite a long time in an exam situation. So they're saying just do it for vertex A. Okay, so delete A. So get rid of this and all of the lengths which are incident to it. So this one, and this one. So that's what we're going to have. So let's draw that out. I'll tell you what. Let's just do it with this one here, and then. Okay, so then we've got this, and this have disappeared. Now find a lower bound by deleting it. So now we need to find a minimum spanning tree, and we can use either Prim's or Kruskal's algorithm for that. Let's just do Prim's. So let's start at B. I'm going to add the length of 4. Then to C or B, the lowest length is 6. I'm going to add the 6. Then to B, C, or D, the lowest length which doesn't complete a cycle is 7. And then I've only got one option left to connect F because A is not included in this graph now. And so we're going to include F. So that's our minimum spanning tree which we've created. And now let's go to add in the two lengths from A. So you can see we've got length 5, 4, and 6. And they're saying just add in A with the two smallest lengths here. So we're going to add in by 5 and 4. Okay, so we're using the two smallest lengths there. Now we've come up with a lower bound here. So the lower bound is now going to be to do the 4 plus the 6 plus the 7 plus the 8, which was the spanning tree measurements, and then add in, so going to add in here the 5 and the 4, which were the two additional lengths to add in from A. Now, this always guarantees a lower bound. So it guarantees a lower bound. Why? So this guarantees a lower bound because you definitely have to have 6 edges that make a Hamiltonian cycle in this case. So going from A to B to C to D to E to F and back to the start again is going to be 6 different lengths. Okay, so that we could go around the outside for that one if you wanted to. That would be a Hamiltonian cycle. So we definitely need 6, and we found the 4 best that we possibly can with 5 of the vertices. So we've got the lowest amount possible with 5 vertices, and that's the minimum spanning tree. So we can't get better than that to connect those five vertices up, and that's not necessarily going to make a path or a walk. That's going to be a tree potentially. Like in this case, it actually is a walk around there, but it could have gone like this instead, where D had several going out. So it couldn't be included in part of a cycle. So that's definitely the best option that we could have had from connecting 5 of the vertices, and this is the best option that we could have of connecting A to that network as well. Now, it's possible that actually gives us a viable Hamiltonian cycle. In this case, clearly it didn't. But if it gave us a viable Hamiltonian cycle, then we've also found the lowest possible Hamiltonian cycle, or the lowest possible route for the traveling salesman. But the likelihood is that we're not going to find that. We're just going to find a lower bound. So what have we done? Let's just recap. We found the lowest possible amount for connecting 5 vertices by using a minimum spanning tree, and we've used the lowest possible connection for going through the final vertex as well. So the lowest plus the lowest is not necessarily going to make a Hamiltonian cycle, but if it does, then we found the optimal solution for the traveling salesman problem. And if it doesn't, we've just found a lower bound. Now, of course, you can go through this process with B and C and D and so on to find a lower bound, none of which are potential routes. So although we've got this lower bound and we've got an upper bound from the nearest neighbor algorithm, remember this one is called the deleted vertex algorithm, the upper bound is actually a viable route. The lower bound is not a viable route necessarily. It could be if it ends up giving us a viable Hamiltonian cycle. Now, again, the best lower bound will require us to do this 6 times over in this case. So this may or may not give us the best answer, but a better lower bound would actually be higher. So it seems like the wrong way around potentially, but if we do this again and then get a higher value, then we still know that we can't beat that, but we could find potentially that this could come in. Whereas the upper bound, if we're starting and finishing at the same place, we only have one algorithm there, which gives us that fixed value for the upper bound. It's possible that we can find better upper bounds, maybe if we're allowed to start and finish at different places. Okay, but if we could potentially bring these in, there is a potential solution somewhere here. We definitely know that this exists. We don't know if this exists, but there is a potential solution in between, which could be beyond our computational power as soon as the number of vertices increases dramatically. Okay, right, so let's have a little look at how they've done it. There we go, they've done exactly the same thing. They found the weight of the spanning tree of 25, and they've added back in the 2 deleted edges here, and so they've got a total of 34. So they've done the same thing as well. Obviously, in an exam situation, you might need to draw out the 2 graphs, or you might need to show how you've connected the things as well, to the spanning tree and the final connections as well. So you're going to need to make this clear in an exam situation, which potentially my graph here wasn't all that clear. Okay, so although I did the process, you're going to have to find a way of showing your steps as to how you've connected these things up. Okay, right, there we go. 15J, last exercise in the book. Give it a go. And beyond that, you've got the chapter summary, the chapter review, and beyond that, exam style questions. Right, okay, well, thank you for listening in, and good luck with the exercise.